There you go. So, in this case, we are talking about rotational motion. So sometimes rotational and circular motion may look very similar, okay? But there is difference there. So this is circular motion. So why it is circular motion? The object here, we can replace this object as a point object and make free body diagram for this to describe that motion, okay? In circular motion, that's what we do, okay? But when we have rotational motion, what happens? We have extended object. And this thing is rotating, and we don't replace this object by a point. Rather, we replace this by a line, as you've been seeing, right? So that's why we have to go through this finding lever arm thingy, right? Because where we apply force matters. So that's the main difference, how we deal with the circular motion versus the rotational motion. So now, the rotational motion, to describe rotational motion, we have all those concepts we learned so far. That's going to be used. So when we apply torque, what happens? It goes through the acceleration, means the speed is changing, and that speed is going to be angular speed, rotational speed, okay? So how is that changing? And how is that related to, let's say, angular acceleration in time and so on? We can use the same idea we use for the linear motion, okay? But there is difference. For example, if something is, let's say we had something, some object here, and let's say a particle of that object that's moving, rotating something like this, then we can describe that and relate that motion with the linear motion V through these, and those we already learned in circular motion. So when we just pick one, just part of that object there at one point and consider, so let's say I have this whole thing that is rotating, right? So now what I'm doing is I'm just taking the cap of this one. Oh, this thing is stuck. So only cap, let's say when it's rotating, cap is also rotating. Now, if I'm just looking at cap, it looks like a circular motion, right? So that way I can relate them. So how the linear speed of this one in the circular path is related to the whole angular speed of this thingy. When I want to relate those, I can make that kind of relationship, okay? So this we learn in circular motion, and that's how we define the angle in radian, right? It is just the angle made by the arc length equal to the radius, right? So we define something like this, and we said, okay, there is this relationship between them. S is equal to R times delta theta. So think about this as a review. We did this exactly in the circular motion as well. But now, this is going to help us to connect the angular displacement and the linear distance. So this is like a linear distance. This one travels when it goes from here to here in terms of angle. That's the angular displacement. Okay. So now, when it is going something like this, what happens is, so why angular displacements comes out handy? So when we think this cap and the body and the tail of this thing separate, then what happens is, in terms of V, they are moving at different speed. V is different at different points. It's moving faster than this point, and so on, right? So the speed is larger and larger here, V. But in terms of angle, what happens? When it goes from, let's say, straight up to sideways, that's 90 degree. Every point here, they went through the 90 degree. So it's a constant. That's the same for all points. So V is changing for each of these points, but the delta theta is same. So that means the omega also becomes same because all of them take the same time. So that's why it's handy to talk in terms of angular speed. That's going to be constant. So now we can combine this delta theta, which is S over R over here, and relate that with the speed. Okay. So how are they related? Just B is R times omega. S is R times angular displacement. V is R times angular speed. So it's the R that's relating the quantities in rotational angular description versus the linear description. Okay, so that's how they are related. And same thing goes with the acceleration as well. So I can use this velocity here, the relationship between them, and use that and come up with this equation. So if you don't understand this derivation, you're going to be still fine. Okay, but we're going to be using this relationship that you need to keep in your mind. Okay, so now with this, what happens? We can go from these linear quantities, right? So linear speed and linear acceleration to the angular one. So how do I do it? So this is V, and we know V is R times omega, right? So if I want VF, then I can write R times omega F. And remember, it's moving in circle means R is same. So R is not changing, so VF, V changing because omega is changing, or they are directly related. So I can write R times omega F here. Now there is no X and Y direction, so we can forget about that. Okay. And same thing here, R times omega I now, right? Pi is R times omega I. So I can replace F by I. And I can write like this. And same thing goes with the acceleration. So acceleration becomes R times alpha, and time is same for both kind of motion. So you can see now there is R, there is R, there is R. So I can cancel those. So once I do that, what happens is now the final angular speed is related to initial angular speed and the angular acceleration by same equation. See, they are, rather than saying same, I should say equivalent, similar equation. So if you remember this, now you can remember this. But of course, you don't have to remember. It's in formula set. But how do you use this equation? Just use the knowledge you used in using this equation, these equations. Okay, it's the same thing. So think about this as a final speed, this as the initial speed, and this as the acceleration. But just add, this is for the angular motion, rotational motion. Okay, so angular speed, angular acceleration. Only that's the difference. Okay, but the equation is same. So we can go and convert all these equations like this. Okay, so those are the linear kinematics. So we are starting from kinematics. See, we are going back all the way to the kinematics. We started from kinematics, and now we are back to kinematics, but this is for rotational motion, not the linear motion, rather it's the rotational motion. So this equation, yeah, you don't need to worry about this one. It turns out sometimes handy, but we don't need it. Okay, so mainly these three equations. Okay, so now here is question. So how do you use that? How do you decide which one to use? So it's the same thing. We learn for the linear motion while using kinematic equation, you note down what are the things you know and what you need to know. And based on that, you decide which equation to use. And if there are more than two unknowns, then you need to use more than one equation. So you cannot solve in one step. Okay, so that's how that thing works. So now,
Dr. Dungana, there's a couple students asking to go back. I think they had a couple questions, I think, before this question. It's in the chat.
And just let you know, the thing you see on the slide that I'm not writing but already there, they are on a posted lecture note. Okay, so even if you miss something here, you can always go back and look at there. So now let me open this poll, and I'm giving you 2 minutes for this. So remember, one revolution is 360 degree. Okay, so this equation may not have exactly the number of revolution, but if you can find angle, then you can find the number of revolution. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see how did we do. So number of revolution means we want, so by the way, number of revolution can be written in terms of angle, just in case. N is delta theta over 360 degree. If you have this in degrees, but remember, we use in radians, right? So it's better to write delta theta over 2 pi. So if you know delta theta, you know number of revolution. So that means we are looking for delta theta. So now, which equation to use? So we know starting at rest means omega I is 0. That's what we know. And the acceleration, angular acceleration, alpha is known, 0.2. And how many revolution has gone through in 5 seconds? So time interval is 5 seconds. So we know omega I, we know alpha, we know delta t, and we want delta theta. So these 3 equations have delta theta in them. This one doesn't. So let's forget about that. Omega I 0, it's going to be 0. Alpha is known, delta t is known. So it looks like we can use that. Here, omega f, we don't know. So that's why we cannot use it. Omega f, we don't know. That's why we cannot use it. Okay. So that's why B is the correct answer, just like most of you identified it correctly. Okay. So now let's take a look here. Let's ride on the bicycle. 1 more minute. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got. So omega L is smaller than omega S. So a smaller one, smaller is spinning faster, right? So that's what happens. I don't know if you have paid attention or not, but that's how it works. So what happens? This is connecting this, means it's fixing the speed. Both of them are moving through the same speed. I went to the wrong slide. So what happens is that I think the another question is there. Yeah, it's talking about the speed. So let me let me decide. Let you decide, you guys. Okay. So minute for this. Thirty more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, well, let's see what happened. This one was tough. So speed, so when it's talking about angular speed, it says angular, right? Now it's talking about speed, means we are talking about v, okay? So linear speed, how far they translate, how far they move, okay? So that's what it's talking about. So think in terms of, let's say, it's going to be easier to understand if we think in terms of, let's say, although these different components are spinning differently, everything is moving the same speed, right? So for example, this is part of bicycle. So bicycle is moving with certain speed. That means everything is moving with the same speed. So that's one way to look at it. Another way, if you want to look at in terms of formula, then what happens? V is R times omega, right? So now what happens? This smaller one has smaller r. R is smaller, right? R is smaller. So although it has larger omega, being smaller r, what happens is B becomes less now, although the omega is large, okay? So a smaller r makes this V smaller. But for this one, r is larger. So although the omega was smaller compared to this, what happens? This r larger makes the v relatively larger. So that way, both of them, the speed-wise, becomes constant. So if you think in terms of, let's say, motion of this ladybug here, let's say in 1 second, this ladybug goes from here to here. So that's going to be the s. That's the linear distance traveled, right? And how far this ladybug going to go? Exactly same distance in this wheel, okay? And so same time, same distance means speed going to be same. So yes, it's not obvious. We need to think a little harder here. Okay. So now we're done with kinematics. Now it's time for Newton's law. And last chapter, we talked about equilibrium. When net torque is 0, what happens? The angular speed becomes constant. That's what we talked about, right? So now, how do we relate the acceleration, angular acceleration? So for that, we can think about, this as a particle. So again, out of this whole thingy, we are just interested in just like a cap I talked about, okay? So now, when it is going like this, what happens? It has a linear speed. And if we know that linear speed and radius, we can write the acceleration as v squared over r. Similarly, we can say, okay, in one rotation, it goes through 2 pi radian. So that's the angular displacement. And if we know time, and then that's going to be angular acceleration, right? So it has both of them. And we can connect those two worlds by using this here. So force. Now for the rotational motion, we need torque. And we know torque is R, means lever arm times force in this kind of situation when these are perpendicular. So now I can replace F by M times A. So when I do that, what happens here? It becomes M times RA, R times A. So we are going from linear, oops, wrong way. We are going from linear to angular. So that means we want to go from A to alpha. So how are they related? We learned that A is R times alpha, means alpha is A over R. So I can replace this A by, I don't need to do that. I can just replace A by R times alpha, right? I want to just get rid of this A. So it's going to be R times alpha. So that's what I'm doing here. And since there is one R here, another R here, it becomes R squared. So just like how the motion depends on both force and distance, and that's the torque, right? Similarly, what happens is motion do not just depend on mass. So here, the acceleration simply dependent on, like mass and force. Similarly, if we look at here, it's not just depending on mass and the torque, rather also the distance. So this R thingy keeps on showing up. Now it's not just R, but R squared, because it came from two places. One going from A to alpha, another one going from, torque to force. So now we can write this equation like this, equivalent. So force is equivalent to torque, and linear acceleration is equivalent to angular acceleration. That means mass is equivalent to I. And we call, since the mass is inertia for the linear motion, similarly, I is the rotational inertia. okay? And we sometimes call it moment of inertia as well, okay? Moment of inertia or rotational inertia. So when we have just one mass at a distance r from axis of rotation, rotational inertia of that mass is mr squared, okay? So that's what that is. But what happens when an object is rotating? It's not just the cap that is rotating, this whole thing is rotating. So we need to take account of this whole mass. So we need to divide this whole mass into a small mass, mass of the cap, and mass of another portion, mass of another portion, and write mr square, mr square, mr square for all of them and add them together when we have this extended object rather than point object. And that's what we are seeing here in the next, okay? So now Newton's second law for the rotational motion becomes, see, looks very similar. You just replace the linear thingy by the rotational thingy. What does it mean? Rotational counterpart of force is torque. Rotational counterpart of linear acceleration is angular acceleration. Rotational counterpart of mass is rotational inertia, which is I we are using. So I don't know if that was for me. It looks like accidental microphone on. Okay, I'll just keep moving. So when we have different masses, and if they are regularly spaced like this, we can write something like this and add them together. So in short, I can write something like this. Okay, so see, this being the axis of rotation, this r is the distance of mass m1 from the axis of rotation. R1 is that, and same thing goes with the R2. So we are multiplying corresponding m and r square. And that's what I am doing. This mr square for one mass, mr square for another mass, and so on. So if you have 4 of them, you write like this. And in short, we can write like this. But if we have many of them, then what happens? We can say, okay, I goes from 1 to all the way, whatever number n is. Okay, so we can just keep adding them. So proper treatment of this kind of situation requires calculus. For example, let's say if I have a disk like this, then I have several of the masses. So this term gonna be several, hundreds of them, right? Becomes a bit troublesome. But the calculus gives us tool to calculate that. And since we don't use calculus in this class, what we do is we don't worry about how do we get the result. But as long as we have nice regular shape like this, what happens? We are given the value of I, or the formula for the I for these different shapes, okay? So for example, this we call disk, okay? It's like it is a disk. So when we have a situation like that, in this case, rotational inertia becomes half total mass times r squared. So think about it. So when this is sitting right there, r is 0, means rotational inertia going to be 0 for the mass that is near the axis of rotation. When it is there, it's going to be maximum mr squared. Now, this half is like an average of maximum and 0. You know, we can think in terms of that. But of course, proper calculation requires calculus. We won't worry about, calculating for this kind of shape. Rather, we have the formula for I for this different kind of shape. And we're going to be mostly dealing with disk like this, and ring means all masses are at equal distance, so it's going to be just mr squared. For the disk, it is half mr squared, and for the ring, it's going to be kind of mr squared kind of situation. Or is it like that? Think about that. I may have a question for you. and you have a minute to answer this question. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got here. So we got hoop, but we also got, okay, same versus disk. So for the hoop, what happens is, see, all masses are at r distance, larger distance. Larger the distance the masses are, what happens? They become difficult to rotate, okay? If I have a shorter one, it's easy to rotate. The longer it gets, what happens? It becomes difficult because there is R factor. Remember, larger R. And you may think, oh, R is same for both of them. How come R is large? But remember, when we calculate that, we divide this into a smaller portion, right? So most of them are at a smaller distance R, smaller than R. But for this, all the masses are exactly at R. So because of that, rotational inertia here becomes mr square. But here, just like I said in previous slide, it becomes half mr square. So if mass m and radius r are exactly same, a disk has a rotational inertia half compared to the hoop, okay? Hoop, all masses are at larger distance. So because of that, it becomes larger rotational inertia, okay? So I see there is a question on the chat that says, how about the sphere? So we can think about this as a disk as a, you know, like solid thingy, and hoop as a hollow disk, let's say, okay? Similarly, sphere can be hollow like basketball, and this is not a basketball, this is soccer ball, right? What I would call football, but in America it's so different. So anyway, so this is hollow, right? And for example, bowling ball, I think it's a solid, it's not hollow from inside. So depending on whether it's hollow or not, what happens? The rotational inertia becomes different. Just like we saw here, solid disk versus hollow disk. They have different rotational inertia. Similarly, this sphere has also, you know, different values. So this sphere and all of them have mr square kind of situation, but for the example, you know, like one kind of a sphere is going to be 2/3. And I see one hand over there.
Yes. Hello, hello. All right. So just so I'm clear on my understanding of this, if we had a soccer ball that weighed as much as a bowling ball, or a bowling ball that weighed as much as a soccer ball, the bowling ball would have the lower moment of inertia than the soccer ball, because the soccer ball has all of its mass tied to the outside, whereas the bowling ball has all of its mass equally distributed. Is that correct?
Right.
Thank you.
That's right. Yes. And depending on whether it's a solid or hollow, it's going to have different values, and hollow going to have larger as long as they have same mass, just like, you know, Robert said, all right? And for one, I think it's 2/3, and another one, I think it's a 3/5, 2/5 and 3/5. Oh, I'm forgetting that. So we need to double check on that, okay? Yes, one is 2/5, another one is 3/5 or something like that. Okay, it's not 2/3. Yeah, sorry, that 2/3 is not correct. I don't know where I got that. Okay, so 2/5 versus 3/5 means 3/5 is larger, so that means it's gonna be, you know, the solid gonna have hollow gonna have the 3/5. And I hope my memory is working, but if it's not, of course, we can find that on the book, okay? The correct one. But they have different values, I know for sure. So now, let's say, how do we use Newton's law for a rotating object? So in this diagram, we see a kid is pushing something like this. The force is acting something like this. And this thing is rotating about this axis. So there is this torque due to that force. So that's R and that is F. Another kid is not seen here. So another kid, which way you think the another kid is pushing? This way or that way?
They are each pushing in opposite direction of each other.
So that means, I'm guessing you mean this, right?
No.
No?
I mean, it should be. I would hope so. But I don't see that in the question.
It doesn't?
No, it says that they each push in the opposite direction with a force of magnitude of 10.
Oh, it did not say opposite direction. It says opposite sides. So one side versus opposite side. So think about this, right? This, let's say, I can replace that disk in free body diagram by a line. And now one kid is pushing this way. And if they want to rotate it, what has to happen? The torque due to both of them has to be either clockwise or counterclockwise. If one is clockwise, another one is counterclockwise, what's going to happen? One torque going to be positive, another one going to be negative, and net going to be 0. If the disk is not rotating already, then it's not going to start rotate. And if it's already rotating, it's not going to be very helpful. It's just going to keep rotating with the same speed. It's not going to speed up, okay? So what happens is they each push in opposite direction. Oh, there is opposite side versus opposite direction was there. Okay, Robert was a little bit ahead of me there. Okay.
Yeah, I was reading, just just very slowly. Read slowly.
Okay. Yeah, I'm sorry. I kind of shut you off. It was there. Okay.
I knew what you meant, but I just wanted to make sure I was clear. That's all.
So,
thank you.
Yeah. So here in this question, opposite means like one is pushing, let's say east, means another one is pushing west, right? So if I were to draw a free body diagram, it's going to be easier if I do this. If this is like east, let's draw like it is, right? So this is east. That's going to be west. So that's what this opposite direction means here. Yes, opposite side and opposite direction. Okay. So now what happens here? This is the axis of rotation, right? So that's the axis. So this wheel is spinning about the center. There is a pivot at the center, and that's where this merry-go-round rotates about, right? So that's the axis. So now if this is radius, that's going to be R. R going to be the lever arm for that force, right? And same thing goes here. And both of them are applying same amount of force. So F is 10 Newton. And if the merry-go-round has mass 180 kilogram and radius 2 meter, what is the angular acceleration? So now, think about this. In our linear motion, what happens when we have force and when we want acceleration? We can use force is mass times acceleration, right? So there is mass, but it's not talking about our regular acceleration. It's talking about angular acceleration, which is alpha. So that means alpha is related to torque. So what we need is we need to use torque is equal to I times alpha. But since there are two torques, we need to add them together. See, torque due to this force and torque due to that force. We need to add them, okay? I is rotational inertia. And in this case, this is a disk. It says assume it is uniform disk. By telling that what it is telling us, what helpful information it is giving us to solve this problem, you think, by telling us it's a disk?
It would be telling us that the mass would be evenly distributed.
Right. That means the rotational inertia in this case is going to be half mr squared. So that's what it is telling us. Yes. Okay. So see, M is given, R is given, means we know I. Now the two forces and this lever arms given means we know torques. All we need to do is find the total torque is equal to I times alpha. So that means that we can find alpha. So it's like using Newton's law. Net force is mass times acceleration, right? And to find net force, we did draw a free body diagram. At that time, we had just point. We replaced object by point because we are talking about going from one point to another point, one place to another place, translational motion, okay? But here it's a rotational motion. So what's the difference? Rather than using dot, we need to draw this because R matters here. How far the force acting, it matters. So we replace that, okay? So now with that, see the torque due to this force here, gonna be R times F. And is it trying to rotate which way? Clockwise or counterclockwise? Looks like it's going counterclockwise, means it's positive RF. And how about this one that's acting to the east? It is also trying to rotate counterclockwise, means it's going to be positive, and value is exactly same, R times F. Both forces are equal and they are at equal distance. And these kids being wise, they are not pushing in, but rather pushing sideways, okay? And that way it's going to spin faster. They know it, okay? So that's why it's going to be that. So that's the right-hand side. So just like when we used to have something like that, when we have normal force like this, mg like this, what did we do? We did sum of force as n minus mg, right? N, assuming that's positive, plus n minus mg, sum of force, right? Same thing, we are doing same thing, but this time it's not just sum of force, rather sum of torque. Don't forget R. Sometimes I see students forget about R. They just tend to add force, okay? So distance matters for the rotational motion. So don't forget about R. So that's why we need torque, okay? So with that, Now we can solve for alpha. So alpha is 2 times RF over I, and I is half mr square, means it's going to be 4 times RF over mr square. You don't need to simplify, you can just plug in numbers right here and get the answer, okay? And we know the unit going to be radian over second square. That's how we use it, folks. See, that was Newton's law. And after Newton's law, dynamics, what did we do? We did work and energy concept. Do you guys remember that? Net work done is equal to change in energy, right? So work kinetic energy theorem. So same idea here. So we can go through this and get the same equation here by using this kinematic equation. Net work done is equal to, it's like half mb square, but v here is final minus initial. But of course, this is not linear, but it's spinning, same idea, okay? So we can open this and we can write this as kinetic energy, final kinetic energy, initial kinetic energy. Just like we had half mb square, we wrote that as a kf, right? It's the same idea, but remember, this is different because this, for example, the merry-go-round is just spinning in one place. It's not moving from one place to another place. So in that sense, it doesn't have that V, rather it has omega, but it has kinetic energy. That kinetic energy is the rotational kinetic energy. And rather than just saying kinetic energy, we say rotational kinetic energy. So there is a difference there. It looks very similar. So this is equivalent to m, this is equivalent to v. So it's like half mb square, but it's for the rotational case, okay? So we are just bringing all those ideas together for the rotational motion. Yes, we can systematically derive it. If you are interested, go ahead, look at it, okay? But this is what matters. So now we have one more kind of kinetic energy. So here, this object can just spin in place, and it has kinetic energy. What kind of? Rotational kinetic energy. Or this object can just, let's say, just slide, means it has translational kinetic energy, half mb square. But when this object is rolling, when it's rolling, what's happening? It is moving from one place to another place, means it has linear speed, just like car. Wheels of the car, they are spinning, right? But they are moving with the car. So they have linear speed, same as shown by the speedometer. And similarly, they are also spinning. So they are spinning means they have rotational kinetic energy. They are moving means they have goodwill kinetic energy. So they have both kind of kinetic energies, rotational and linear or translational, okay? So now total kinetic energy of object could be sum of these two. Remember, we use just one kinetic energy so far, half mb square. Whenever it said kinetic energy, half mb square. But now if object is spinning, we can have one more term in kinetic energy, okay? The translational is our good old, and this one is new one. And if object is not spinning, then of course, this is 0. But if it is spinning, then this is not 0. If it is just spinning, not moving, then this is 0. Spinning in one place, like merry-go-round. Half mb square is 0, but it has half I omega square. But if it is rolling object like wheel of a car, that means it is moving at the speed of car, it has this, and it is also spinning. It has this as well. So both of them, okay? So yes, linear speed is same as translational. So far, we did not differentiate them. We simply say the speed, okay? So yes, we're gonna still keep on saying this as a speed, but sometimes you may hear this word translational speed, which is just linear or just our good old speed. But rotational always has name, rotational speed, okay? So let's keep that in mind. And looks like we are out of time. So next time we'll pull on this one, okay? Okay, have a good day. I'll see you on Wednesday.
Thank you.
Thank you.
Thank you.
Thank you.
I'll see you later, Dr. Jungana. I'm going to take off. Have a good day, and I will talk to you on Wednesday. Bye.